Hello everyone. Today I'm going to share this video with you because this Friday we are going to the Nelson Labs to work with the ETAP software. So I'm going to provide some introductory material before we get there. If you go to the Moodle page for your module, Fundamental Methods in Civil Engineering, and scroll down to Resources and Materials section, you will see there are two tabs here: ETAP's Verification Examples Analysis and ETAP's Verification Model Analysis. If you download these two tabs, you will see you will come up with a couple of files in each. And for example, for the ETAP's Verification Examples Analysis, you will have 15 individual PDF files, and each one is for a specific example which the CSI company has created. So there is a specific example in each one, and you will compare the ETAP's results with the analytical results which are available in hand. For example, today we are going to focus on example 1, and if you open the PDF file, you will see example 1 is about plane frame with beam span loads for static gravity load analysis. If you scroll down, you will see the shape of the structure. This is a 2-bay, 1-story 2D frame. You have 3 columns and 2 beams. You have 2 cases of loading. Case number 1 consists of 5 concentrated loads, as you see, and the case number 2 is a kind of distributed loading on the beams. And you have here the module of elasticity is 3000 KSI, and all the beams are 12-inch by 24-inch, and this is for columns, and the beams are 12-inch by 30-inch for the height. And if you go to the second folder you get from the Moodle, this is a set of files with the extension of EDB. EDB is a kind of file that the ETAPs work with, and each one is created by the CSI company for validating the ETAP software. So as you see, for example, here, today we are going to use example number 1. So I just grab my folder and go to ETAPs. If I open a file in ETAPs, and example number 1, if I open it, after a few seconds I will come up with 2 different windows showing my structure. As my structure is a 2D, I don't really need two windows, and I stick with 1 window, and it shows everything to me. And if I go to the elevation, so I can see my structure, and there are 3 columns and 2 beams. And if I just right click on one of the columns, you see that section properties CP1, and let's see what is CP1. For seeing the definitions, you need to go to the define menu at the top, frame section, section properties, and frame sections. All of the frame section definitions are here. So because I have 2 monitors, for some reasons when I open something it goes to the second one, and I just grab it and bring it back just to be in the video. CP1 is here, and if I modify show the property, you will see that it uses the general section shape, which is a kind of section that you need to enter the section properties manually and don't care about this circle section. This is not the case. And you need to enter the properties manually. Everything is 0 rather than the moment of inertia. This 13,824 comes from the section characteristics here. This is the column section property, which is 12" by 24". So the moment of inertia is 1/12 multiplied by 12 multiplied by 24 powered 3. So this is, if you calculate that, you will come up with this number, 13,824. And the area is set here as a very big number because the author of because the author of this example needs to just take into account the bending moment effects and not the axial force or shear forces. That's why they put just a big number here, just to make the axial deflections very negligible. But it doesn't matter, you can put the actual area if you want. And this is the MP1 as a material. We'll take a look at MP1 to see what is MP1 as well. But before that, just take a look at BP1, which is the section property for the beams. If you modify show the properties, again, they have used a section shape of the general. And here you can see the section properties, and this is 27,000 for the moment of inertia. And this comes from this fact that the beams are 12" by 30". So the moment of inertia is 1/12 multiplied by 12 multiplied by 30 powered 3. So if you calculate that one, you will come up with 27,000 for the moment of inertia. So let's take a look at the material as well, because that's important. If you go to the define and material property, the first one, this window shows the steel, concrete, and some others. The MP1 is created by the author. It's not the default of the program. If you go and select MP1 and modify show the material, you will see that this is a concrete isotropic section, which has 0 for the weight and mass, because I don't want to weight and mass contribute to the analysis. I just want to proceed with the load cases 1 and 2 that's provided in the example. And the module of elasticity here is 3 million pounds divided by square inch. So it's coming from here. The module of elasticity is 3000 KSI, which means 3 million pounds per square inch. So this is the material, and also I can go here, this tick, small tick, and if I press that, I will see here, I just tick end releases. End releases helps you to see what hinges you have in this structure. Here we have 3 different hinges. If you take a look at this structure, here you have hinges 3. So we want to be exactly like this system. So if you want to define these, for example, if they are not there, you need to select the the element you want to release the moment at the end, and go to the assign frame, release partial fixity, and you can release the moment at one start and or end, whichever you want. If you tick these two, it puts a hinge at the start point of the element. If you put these two ticks, it puts a hinge at the end of your element, and if you tick 4 of them, it puts two hinges at both ends. So try to use this option as well. And also let's take a look at the loading. There are 2 cases, case 1 and case 2, as you see. So if you go to the display and load assigns to the frame, there are 1, 2, 3, but we are using just 1 and 2. Show the loads in case 1. You see these are the concentrated loads, and if you go to the display frame, show me the case 2, which is this one, the distributed load. The amount is 833, but if you take a look at here, it's 10 kips per foot. So if you change it to inch, it's 10,000 pounds per divided by 12. You will come up with 833 pound per inch, because your dimension system is pound and inch in this example in the software. So also take a look at load patterns. You will see, just focus on the first one and the second one. These are just names. You can just modify the name here. But the first one is representing, like, let's say the dead load, and the second one representing the live load. These are the load patterns, and also load cases. You have load cases. The loads 1 and 2 are linear static, which means they are first of all static, and they are linear. There is no non-linearity. And you can have also load combination here, just to combine your loads if you wish. For example, comp number 1 can be load number 1, and etc. And if you scroll down in the PDF file, you will see a table like this. This is for comparison of results for beam B1 in case 1, and it provides some bending moments and shear forces at ends I, J, and some middle points from ETABS and from theoretical solution of the example. And you see that the obtained results are really identical. So how you can get these numbers? You can go to your model and run your model, run analysis. So you need to wait a few seconds or a few moments for the software to be done. And after that, you can get the internal forces. So this is the deflection shape of the structure. We anticipated this kind of deflection. We have symmetry in this structure, so everything is symmetric, and For example, here you can give the deformation, and here you can display the different internal forces. If you don't like to use these icons here, you can just straightforward go into display and use the deform shape or force stress diagrams like frame, pier, spanner, link forces. This can be used to show the internal forces. So in the case, load case number 1 here, I want to see the moment 3, 3, which means the major moment, the moment along the major axis. And I just press OK, and you can see here that in the middle, for example here, you can right click on that, and you can get the moment. For example here it is 3 million pound inch, and it is here, it is without dimension here, but it should be yeah, this is in the middle of the beam. Bending moment in the beam is 3,375. This is kips, should be. As you see here, see it's this point. So you can get all of these numbers from in a table and export it to Excel as well. So this is the moment M3, the major moment, and this is the shear along the, you can see this beam is blinking. So this is the moment, this is the shear, and this is the deflection, and you can just move and see how it varies over different points. And as you see, this is the external force, and these are the forces at the both ends of the beam. And in the left hand side you don't have any moment, internal moment, because as you know you have a hinge there, so the internal moment is 0 obviously. You can go and compare these results point by point for bending moment, for shear, for different points, and from ETABS and from theoretical solution. This is for the case 1 and the beam B1, which is B1 is this beam and B2 is this beam. C1, C2, and C3 are different columns as well. So this is the case, load case 2 for the distributed loads for B1 again. This is again for the B1 load case 2, continues for the shear forces, and that's it. It just compares the loads, the internal forces of the B1 beam in load cases 1 and 2. So you can really elaborate more with this model and try to make it from scratch on Friday. And if you face some problems, we will discuss in the lab and we will try to solve it. It helps for you to get more familiar with the ETABS and to learn where different options are in different menus. And that's it for today. Let's see how it will work on Friday. Thank you for your attention and have a nice day.